Okay, today we're going to talk about commodity prices and a little bit about what kind of models you can use to model commodity prices. We've already talked about autoregressive moving average models, and we're going to talk about a slightly different kind today as well. So if we're talking about the energy industry and we're talking about commodity prices, we're really mostly talking about fuel. So that can mean petroleum products, but that doesn't apply as much to the electric power industry. In the electric power industry, we're really thinking about coal and natural gas, and really mostly natural gas. And we'll talk about why coal prices don't fluctuate that much, but the really exciting part is the natural gas. And that's from the perspective of a utility, right? You can also think about electricity itself as a commodity, and the price of electricity depends on a lot of things, obviously, demand being one, but also fuel prices. So fuel prices end up getting passed through to electricity prices, and not every part of the United States has a wholesale market for electricity that we could think of as a commodity market. For example, in North Carolina, the price of electricity we only really recognize on a retail basis, and that can fluctuate year to year, but it's pretty divorced from a lot of the fluctuations that you would see in the fuel markets and in other wholesale electricity markets in other parts of the country. So we're going to go through some of the basic drivers of what influences prices for these commodities today. And we'll also talk a little bit about newer markets for important commodities and raw materials that are used in the fabrication of renewable energy technologies. And these are getting increased attention paid to them because of the growth in renewable energy, and it's sort of like the first time we've collectively looked around and decided, what areas of the world support production of the raw materials that we're going to need to rapidly increase our use of renewable energy and storage technologies, and what markets are in place. And I think there is some concern about the sustainability of those production pathways for those raw materials. And we'll talk a little bit about the organization that tracks those markets as well. So as I mentioned, the price of fuels, whether that's natural gas or coal, tends to have a direct pass-through impact on the price or the cost of electricity from fossil fuel power plants, and that often gets incorporated into wholesale prices and then eventually retail prices for customers. And I think that's when we think of the impact of commodity markets on electricity prices, that's really the most direct dynamic impact that can occur. And we tend to think of renewable energy in general as being sort of immune to year-to-year changes in the cost of electricity. And I think that's true, although you would have to factor in availability as well, because that ends up impacting the levelized cost of electricity. But even within the context of thinking about renewable energy as this long-term stable resource that on a year-to-year basis, you may not know exactly how much you're going to get from a wind farm or a solar farm, but you kind of know how much it's going to cost, because most of the cost of renewable energy is driven by the annualized capital cost. So you make this really big upfront investment, you borrow a lot of money, and then you have a mortgage payment and some fixed operations and maintenance costs associated with maintaining the project. But you're not tied into these volatile commodity markets for fuel that on a year-to-year basis can result in large swings in what the cost of producing electricity is. Still, commodity prices do matter for renewable energy. And often, it can be a little worse, not worse, but um, if commodity prices are altering the capital cost of renewable energy projects, then it's more appropriate to think about those capital costs really being baked into the cost of renewable energy over the entire project lifetime. So there's no chance for the commodity prices to like go back down and lower the price of electricity from a wind farm or a solar farm. If you happen to build a wind turbine in a year where steel and copper prices are really, really high, then the long-term price that you're going to need from selling electricity to make your money back is a lot higher. And that's what these figures show. These show the top figure is just tracking copper and steel prices over the last 26 years or so, and the bottom shows you the different colors represent different regions of the country in which a long-term power purchase agreement is signed between a developer of a wind farm and a buyer, whether that's a wholesale market or a utility. And you can see that the contract price, the dollar per megawatt hour price that wind developers needed in order to incentivize development increases around 2009, 2010, 2011, and that corresponds directly with increases in commodity prices, copper and steel. And so that means that a contract, and these contracts are typically like 30 years or 25 years, a contract that's signed in 2010, because that's when the developer puts the project into place, is going to have a higher price of electricity for the next 30 years, not just while steel and copper prices remain high. So there is an entity that's associated with the U.S. Department of Energy called the U.S. Critical Materials Institute that does track technologies and required materials for those technologies and markets for those materials, specifically with regard to clean energy and other advanced technologies. And they track a couple different important rare earth metals that they think are going to potentially be faced with supply challenges that may limit our ability to rapidly increase our dependence on low cost wind turbines, solar panels, electric vehicles, energy efficiency type stuff. And so if you ever need a resource for understanding a little more about these markets for materials that are smaller but growing fast and maybe less transparent, this is a good place to look. So the Critical Materials Institute focuses on 5 rare earth metals and then 2 near critical materials. And I am not exactly sure what the end uses of these 7 materials are. But the overall aim of this institute is to try to, number one, diversify supplies, which means even for the same material, if one geographical source goes offline, you can rely on a different source. So you don't want to bake in this dependency on one geographical region for everything. And I think this is one concern people have with switching from an economy that's based heavily on petroleum, which, if you look at a map of the world, really comes from a handful of places, to an economy that relies on renewable energy that requires rare earth metals that likewise only come from a handful of places globally. And so I think that puts us in a similar sort of like policy bind where, we have to be interacting with countries that we may disagree with politically or on other grounds. Um, the second really big aim here is to develop material substitutes. So not just diversifying the places that you're getting materials, but actually coming up with new materials that functionally serve the same purpose and either give you an option for relying on something else if one source goes offline, even if it's more expensive, or developing cheaper, better materials than the ones that we already know about. And we also want to use the available materials more efficiently, which means reducing waste, building in an understanding that these are scarce resources to begin with, and increasing to some extent our ability to recycle used products and close this loop of some of these critical materials. And then they also are in the forecasting business, which is a tough business to be in markets that are so new and less transparent, but they take an active role in doing this. So here's the answer to my own question. I said I didn't know exactly what some of these materials were used for, and this gives you a pretty clear idea of that. On the left-hand side, you have all the different materials, and then on the right-hand side, all their applications in renewable energy production, in vehicles, as well as lighting. So they have this sort of system for triaging some of these different materials to understand which are what we call critical, so ones that are worth paying attention to in particular. And there's two metrics for how they decide whether a resource is critical. And the first is whether there's a supply risk, right? So that could be a function of known reserves, or the accessibility of those reserves, or the location of those reserves in countries that hate us, or anything like that. And so that's what's measured here on the x-axis. So the further you go out to the right, this is some sort of standardized way of measuring the risk that shortages of the supply of these materials could take place. And so the red materials have higher supply risk. On the y-axis, they also do incorporate some understanding of how important the material is in the renewable energy economy. So something that would be high risk would have to, or critical, would have to have a high likelihood of, or higher likelihood of supply risk, but also be something that is extremely important on a fundamental level to rapidly increasing production of renewable energy, or batteries, or electric vehicles, etc. And so we can sort of break up all these different materials into three groups. Ones that are at low supply risk and not that important are green. Ones that are high risk for supply shortages and are extremely important in renewable energy are in red. And they also are ranking these according to time as well. The left-hand plot is basically current conditions, what they look at as the critical materials. And then the forecasting comes into play in the second plot on the right, or the second table on the right. They're looking out to 2025. Now, I think it's important to recognize that it's really hard to look past 2025 here. And that's tough if you're Elon Musk, if you're Tesla, or you're any other manufacturer that has the goal of long-term massive scale-up in production. An inability to really forecast resource availability beyond 10 or 20 years is risky. It's really risky. And I think that this is a growing field, I think, in this type of natural resource economics related to a growing renewable energy economy is fascinating. In recent years, you may have sort of heard there is, in 2011, 2010, the prices for some rare earth metals went through the roof. And that's what this figure shows. It's really tough to see. The legend is awful here. Which which color is associated with which metal. Um, but this is just a remarkable increase, and I think this type of price increase over such a short period of time is something that has sort of a ripple effect, not in terms of um, actual financial impacts, although those can occur, but just in how people view these markets. If you're in a market that's capable of a 4,000% increase in prices within 1 year, um, then I think it gives people a lot of second thoughts about planning on the availability of these resources, or the affordability of these resources into the future. Okay, so that's rare earth stuff. Yeah, I wish I could spend a little more time on that. It's such a new field, that I think I don't know much about it, and not many other people do either. But it's very interesting. I think if I were an undergrad and I were interested in economics or engineering, markets for critical raw materials for renewable energy production would be a really cool place to get involved. But we're going to talk about oil some too, and I think oil certainly had an interesting last couple of years for sure, and conceptually, I think we've all sort of grown up with this idea of peak oil and the idea that this is a limited resource that could have significant consequences on global economies if we ever ran into significant shortage without available substitutes. And that paradigm has really been replaced in the last couple of years because of unconventional production of oil in Canada and the United States and other places, that has sort of destroyed this idea of peak oil. That combined with growing energy efficiency, and the increasing risk that electric vehicles and other electric types of transportation will steal a considerable amount of market share away from combustion engines in the near future. And so I think depending on where you read your news, people are more or less bullish or bearish on the future of oil and the potential for countries that rely significantly on producing oil for revenues to keep relying on that well out into the future. I think that's a big concern with a rapid shift towards renewable energy and vehicle electrification, is that we could, in the same way that we're sort of stranding coal country, we could strand some parts of the world that really depend on selling oil to make money. So in terms of crude oil prices, usually, because we get oil from all over the world, they're really sort of viewed as different commodities, and part of that's because if you're looking at buying oil from different parts of the world, transportation cost is a significant part of the cost you pay for the oil. So where you get the oil really matters. And so we name different types of crude oil, or we refer to them by different names, like WTI, West Texas Intermediate, Brent, so the North Sea Brent crude, and this figure here shows that each of these different types of oil, which we refer to basically by where we're getting them, have different physical or chemical characteristics that determine their worth. So on the y-axis you have API gravity, and in general you want to have, this is a measure of how viscous the oil is. And so you want to have the most profitable or valuable oil to have is light oil, so less viscous oil. And then another property of oil is the sulfur content, because many places in the world have air quality regulations that specify that sulfur needs to be removed from crude oil in the processing phase before it is used and before it is refined into gasoline or other products. And so you want to have as low of a sulfur content as possible, ideally. So this figure shows oil prices for two different types: West Texas Intermediate and Brent oil. And you can see that for the most part they're very similar, although there is a period from 2011 through 2014 where they separate, right? And the price of West Texas Intermediate is much lower. And there's, apart from that, some pretty distinctive characteristics of this time series that correspond to significant events, significant global events. So, think about what's happening here in number one. Number one's kind of obvious. Number two is much less obvious, and then number three is a little less obvious. So let's go through what happened at each one of these points. So the first one, obviously, in late 2008, there was the global financial crisis, which dramatically decreased economic activity, and as a part of that, demand for fuel. The number two, where the price for West Texas Intermediate oil was much lower than Brent crude, had to do with an oil glut in the Midwest, in the Midwest United States, from unconventional oil production in the Bakken and in Canada, and the oil could not get down to export markets in New Orleans, and so the price of oil internally in the Midwest became really, really low. The oil was sort of trapped there, and there was a surplus of oil, and it drove the price down. Number three, after the financial crisis, oil prices recovered, and then they really just tanked in 2011 or so. And this was something that surprised many, many people. And there are a lot of different reasons for why this happened. One of the main ones is economic slowdown in China and also Europe. China was really absorbing a lot of growth in China has really been absorbing a lot of the excess oil production for years. And as soon as growth in China stopped or slowed down, then we were left with a lot more oil in the market that drove prices down. On top of that, you have the OPEC price war, and so this is not a war as much within member countries of OPEC, although that is sort of happening. There's struggles among those countries because they're having a really hard time coordinating actions, which is what they're supposed to do as a cartel. But the conventional wisdom has been that OPEC has refused to reduce production of oil in order specifically to keep the price low, in order to run out of business newer unconventional production facilities in Canada and the United States, who are mainly profitable when the price of oil is really high. And so by driving the price low, the goal is to run those guys out of business and preserve some market share for OPEC. But there are a lot of other conspiracy theories about why OPEC may be refusing to reduce production as well. We can also look at the correlation between oil and gasoline prices, and this is mostly one for one. Notice, I mean, these are on different scales, obviously. On the left y-axis is the value of crude oil, and the right y-axis is the value of gasoline. But the correlation between these is extremely high. So there's also historically been a pretty close relationship between the price of crude oil and the price of natural gas. And you may wonder why. And part of it's because in some applications, particularly residential heating, these are substitutes. But also they tend to be co-located in terms of extraction and refineries. So a lot of natural gas can be produced in the process of producing oil, extracting oil, but also a lot of the places where natural gas and oil are refined, even if you're extracting them from two different locations, are co-located, especially if you're talking about the Gulf Coast. Now, interestingly, in recent years, and remember, fracking, the ability to get natural gas and oil out of the ground, this new innovative way of doing that, has opened up unconventional supplies of both natural gas and oil. But the use of fracking in some cases has precipitated this decoupling between oil and natural gas prices, at least observed decoupling, that has been pretty surprising. Although in the long term, I think people expect the price of natural gas and oil to maintain a pretty close relationship. So here's the coupling I was talking about. Natural gas prices are in orange, and crude oil, West Texas Intermediate prices are in blue. And you can see the main coupling happened in the wake of the financial crisis, where natural gas prices really didn't recover. They were both really high up until mid 2008, and then they crashed. And then over 2009 to 2014 or so, the price of oil recovered, and then it crashed in the last couple years as a result of slowing growth in China and the OPEC price war. But the price of natural gas has just continued to drop, really. And this is, keep in mind, despite the fact that our use of natural gas is increasing, both residentially and in terms of heating applications, but also in the electric power sector and other industrial processes. So, to some extent, I think it was the forces that brought the price of natural gas really low have finally sort of caught up with the price of oil. Now they're both pretty low, and I think in general people expect them to recover this sort of close relationship in the future. So gas prices, we pay attention to a lot in the electric power industry because of there's a number of power plants in every system that rely on natural gas, and the way in which they're used, they tend to be used in peaking power plants, and so in many cases they are the marginal unit, the market clearing unit. So the price of electricity can rise and fall based on the cost of electricity from these natural gas plants, and so the price of natural gas goes a long way in determining that. And historically, prices of natural gas have been subject to pretty significant disruption by extreme weather events as well as extreme macroeconomic events. So gas prices tend to peak according to changes in seasonal demand, production of electricity from natural gas plants increases in the summertime, so demand for natural gas increases then, and then demand for natural gas also increases in the winter because it's used for heating, and so that resource can be a little scarce, and in some cases power producers and natural gas suppliers for residential heating are sort of competing on the pipeline for the same supply. Historically, all natural gas prices in the U.S. have been reported in terms of this single trading post, this single trading center on the Gulf Coast called the Henry Hub. And so most EIA prices or natural gas prices are listed in terms of the Henry Hub price. But what's worth noting is that because of the growth in fracking, the unconventional extraction technique, the production of natural gas, and in some cases the refining of natural gas, has shifted to other geographical areas away from the Gulf Coast towards Appalachia, even in western Pennsylvania. And so in recent years, actually most natural gas trading was done at the Dominion South Hub, which is in western Pennsylvania. And so the balance of power in terms of the sort of the correct price to use in terms of representing what the price of natural gas is in the United States is shifting away from the Gulf Coast towards other areas because of fracking. So this is sort of a similar exercise, like what happened here in each one of these points. These are all kind of interesting weather / climate / historical events for natural gas prices in the United States, and these are all Henry Hub prices. So 1, 2, 3, 4, 5, 6. Let's go through them. Number one was the California energy crisis in the early 2000s. Natural gas prices increased dramatically. California was one of the main states in the country that was heavily dependent on natural gas for generation, electric power generation, because of air quality standards. California didn't have any coal plants. The rest of the country, we have quite a bit. And so there were gas price increases because of increased demand. They went through a drought. They didn't have as much hydropower, so they had to increase reliance on natural gas. But also there was market manipulation of natural gas pipelines and facilities by companies like Enron that deliberately tried to cause problems in order to make the price increase. Number two was Hurricane Katrina. The largest increase in prices in the last 25 years was because of reduced refining activities in the Gulf Coast as a result of the devastation of Hurricane Katrina. The increase in natural gas prices in the lead up to the financial crisis was number three. And to some extent this was sort of irrational market behavior. The price of gas was increasing because it was generally tracking the price of oil, even though economic activity was decreasing and our supply of natural gas was increasing because of these unconventional extraction techniques. And then the financial crisis, number four, caused prices to crash. In 2012, number five here is in 2012, natural gas prices reached their lowest point because we had a lot of natural gas in the market. We had excess supply and a really, really mild winter. And then number six, gas prices increased briefly and spiked pretty high because of the polar vortex. You had a situation where power generators and natural gas suppliers for heating were both competing over a supply of natural gas that was insufficient, more or less, to meet both demands because of extremely cold, like historically cold weather in January and February of 2014. And so the prices went up. So I also wanted to introduce another type of model as we transition away from thinking about time series analysis in a more traditional way in terms of autocorrelation and stuff like that, and then time series modeling, so developing autoregressive moving average models, towards thinking about more generally stochastic modeling, so not linear systems, but a reasonable sort of intermediary is this class of model, Ornstein-Uhlenbeck models, that are useful for commodity prices, for describing commodity price behavior. And these are set up a little differently. Remember, autoregressive moving average models assume you sort of describe the behavior of a price in a certain time, over time, or you can predict a price in a certain time period based exclusively on the values in previous time steps. And here we're saying if we're trying to model the price of electricity, which is xt here, we're saying that the period to period change in the price is the first derivative of the price xt here, is equal to a combination of a bunch of different stuff. And I want to go through each part of this equation and explain sort of the mechanics of this. So there's part of it is we're assuming some drift, some tendency to move in a certain direction, whether it's up or down, and then we're including some volatility, which is similar to what we saw in autoregressive models in terms of a white noise process, so some sort of randomness built in. But then we also have inherent in here a really important feature, which is a mean reversion, which means that as prices bounce around, the further they get away from what we assume to be the natural sort of equilibrium mean, the more likely they are to return to it. And so that's sort of a unique feature of this model that's worth exploring. So let's unpack this equation just a little bit. Again, we're explicitly modeling the net change in the price, so the derivative of xt here, and we can discretize this process so that we're not truly taking the derivative. We're looking at period-to-period changes, and we'll do that in MATLAB. So that's what we're modeling, is the change in the price, and we're explicitly saying that that change is a function of, first, the difference between the long-term mean and the current value of xt. So mu is the long-term mean, right? The long-term mean. That's the sort of equilibrium price that we expect over the long term the price to return to. And so you can imagine here if xt is much higher than the long-term price, then you have this really big negative value in the middle of this equation, which tends to force the net change in xt to be negative, right? So that tells you that the higher the current price of whatever this process xt is above its long-term expected mean, the stronger the force of the change is, the downward force on the price. Same goes if the xt here is much smaller than the mean, then you have this positive value in the middle of the equation here that forces the value of dxt to be positive, to recover some value and bump back up towards the mean. And we're also saying that the innovation of this process is somewhat random as well, because we're saying that it's a function of the value d of wt, where wt here is a random walk. And remember, I don't know if you remember, a random walk is a lag one autoregressive process. So it's a process where the current value depends only on the previous value plus like sampling from some sort of random normal distribution. And so if you're just taking the derivative of that, that's basically just saying you're just sampling from a random distribution. So we have mean reversion here, plus randomness in the system, And then we also have some sort of drift here, which is this theta parameter. So we can also, as I mentioned, change this continuous mathematical process to one that's discrete, so where we're talking about separable time steps like weeks, months, days, etc. And so the discrete form of the equation looks pretty similar to the continuous form, although all the derivatives turn into deltas. We still have the main characteristics of the equation that look very similar. So alpha here takes the place of theta, and alpha is the mean reversion rate. So we talked about how the process evolves as a function of how far away above or below the current price is from the mean. So if it's way above the mean, then the process tends to go to decrease. So the value of delta xt here would be more negative. But we also have to sort of characterize how fast we want that to happen. Some processes can be very sensitive to being above the mean, and some may take a longer time to, if they're really high, to drop back down towards the mean. And that's what this alpha mean reversion rate refers to. Mu, again, is the long-term equilibrium level that we're talking about. And then, so that's sort of like the drift process. And then we have the volatility, which is directly controlling the variance of the distribution that we're sampling from, to add some randomness to the process at the very end. And so you can see that the DWT process, the derivative of the random walk or Wiener process, just becomes sampling from a normal distribution with a mean of 0 and a standard deviation that's a function of the time step here times the volatility. And so the parameters we're trying to fit to, we would sort of fit this the same way we would on an autoregressive model, where we have a bunch of historical data and we're trying to figure out the best fit of this general structure of the model for the data that we have. And the specific parameters we're trying to identify are the mean reversion rate, the mean level, and the volatility. And so what we end up with is an ability to come up with synthetic prices that look kind of like historical prices, just in terms of their statistics. So the mean, the variations or fluctuations around the mean, but also the autocorrelation, even though we're not explicitly modeling this as an autoregressive process. So let's go into coal prices. That type of modeling we'll use in class to look at natural gas prices. That's something I've used that class of models for a lot. Coal prices are pretty boring compared to natural gas prices. Coal prices here are in orange, natural gas prices are in blue. The question is why? So here's further evidence that coal prices are really boring. You're sort of zoomed in here on the left. You're looking at only 2 years. You can zoom out on the right hand plot and look at the last 6 years of data, and you do see that coal prices dramatically increased over a fairly short period of time in the run-up to the financial crisis. So in late 2008 you had all fuel prices increasing, coal, oil, natural gas. And then they just all dropped off of a cliff, and since 2009 coal prices have been pretty low. So the main reason coal prices are less volatile is because, at least domestically, historically, we've had a much greater abundance of coal. You can also, and this is a really big one in terms of dampening out a lot of fluctuations in fuel prices, it's really easy to store in advance of use. So you can mine the coal, process it in order for later use at an electric power plant, and then store great amounts of it on site. Whereas for a natural gas plant, that's much harder to do. Months in advance, there might be some on-site storage, but really, a lot of times you're buying natural gas right off the pipeline. The other reason why it's less volatile is because the use of coal is mostly limited to production of electricity. And so the electric power sector is not competing with other sectors for a supply of coal, unlike natural gas, which is needed for both generation and heating. So we started out the lecture by talking about commodity prices for steel and copper and how that impacts power purchase agreements for renewable energy. I also alluded to the fact that fuel prices are directly passed through to electricity prices, and this equation is a demonstration of that. If you're looking at the cost of electricity from a power plant, and we're not accounting here for the cost, the annualized cost of building the power plant, so the mortgage payment. We're just talking about operational costs, which you could make an assumption that maybe operational costs and capital costs are about 50-50 in terms of, and I don't know if that's 100% right, but it's a big fraction. Fuel costs and variable costs are a big fraction of the overall cost of producing electricity at a power plant. So if we're looking at operational costs on $1 per megawatt hour basis, on the denominator here is all the energy that we're actually producing from the plant. In the numerator, we have the fixed O&M costs. So that's the money we're going to have to pay regardless of how much electricity we actually produce, and that could be keeping people on salary, regular upkeep of the plant isn't determined by how much electricity we produce, keeping the lights on, stuff like that. Variable O&M is sort of like wear and tear. So the more you use a plant, the more variable O&M costs you accumulate. And then fuel costs. And fuel costs are also directly related to how much electricity you produce. So the more electricity you produce, the more coal or natural gas or whatever you're consuming, and so your fuel costs increased. And so fuel costs are directly, that is how much electricity you produce times the heat rate of your plant times whatever the price of the fuel is. So that's where a change in the price of fuel would come into determining the price of electricity from a power plant. So let's unpack this equation a little bit more. So again, we're talking about the operational cost of electricity, the $1 per megawatt hour amount. That does not include like the mortgage or the annualized capital cost for the project. So fixed O&M costs don't change as a function of the amount of energy that's produced, but variable O&M and fuel costs do. And let's look especially at fuel cost here. Again, fuel costs you would get by multiplying the amount of electricity that's produced times the plant's heat rate times the fuel price. And so the fuel price here is what can fluctuate as a result of changes in commodity markets. The heat rate is something that's constant, or relatively constant. You can just assume that it is. And this is a measure of the plant's fuel efficiency. So sort of like your car's fuel efficiency, how much fuel input you need in terms of not gallons here, but million BTUs. Do you need to get 1 unit of electricity out? And so efficient power plants would have low heat rates, and inefficient power plants would have high heat rates. And so because the price of fuel here is directly responsible for changes in the cost of electricity from different types of power plants, the market price for electricity also tends to change with the price of fuel. I think what I showed you earlier was that coal prices tend to be pretty stable. but gas prices have historically demonstrated a lot of volatility. And if you look at historical natural gas prices and how they overlap with electricity prices, you can see that a lot of that volatility gets passed through into wholesale markets for electricity. So again, this is not retail prices for electricity. These are sort of wholesale prices, are the prices that our utilities are experiencing when they're going out on the market potentially and buying electricity on our behalf. And so here the price of electricity is in blue and the price of natural gas is in brown. And this close relationship has a lot of really interesting consequences. It has a lot of interesting consequences for renewable energy, especially for nuclear power plants. I mean, if you're talking about the impact that fracking has had on the power industry, it's really not limited to just helping us get rid of coal. It has other impacts as well because of the impact it has on the wholesale price of electricity. So this is something I mentioned before, but kind of glossed over. And this can be a little harder to wrap your head around if you've never had a microecon class. But part of the reason why gas prices in particular influence wholesale electricity prices is because they tend to be the marginal producer in systems. So they're often the most expensive power plant needed in order to meet electricity demand, and those are the plants that set the market clearing price. So if you've taken microecon, you're pretty familiar with this. You have a system supply curve, which is this dotted line, and then the demand curve. Now, this is not specific to the electric power industry because the main difference here in the electric power industry is that we would have a much more vertical up and down demand curve, because people's demand for electricity is pretty inflexible. We really need it, so we're kind of willing to pay any price for it. But the market price here is set by the intersection of these two curves. And we'll talk in just a second about how the supply curve is set. So if we look at the marginal or even variable cost of electricity production at different types of technologies, so hydropower, nuclear, coal, natural gas, oil, you could have solar and wind on here and they would be all the way to the left. And then we stack them. We start with the things that on a dollar per megawatt hour basis cost the least in terms of just their variable cost. Now this does not include the capital cost, right? Otherwise nuclear would be probably higher on this list or further to the right. But you're just talking about once you've built the plant, what's the cost of producing the electricity? This is how you'd sort of order things left to right. And we're stacking, we're organizing all the different power plants we have in a system and stacking them in order of increasing cost. So on the x-axis, as you go across, you have more and more of an ability to produce electricity. So you're getting to more and more of your capacity, your total capacity for producing electricity. And each point on the x-axis is associated with some point on the y-axis, some marginal cost of producing that extra unit of electricity, which is generally the variable cost of whatever technology you're using. So once you go out to about 20,000 megawatt hours, if you're a system and you want to produce that, then that's going to require you to use, and you want to produce that in the least cost way possible, that's going to require you to use some amount of natural gas. And if you go much beyond that, it's going to require you to produce electricity using oil, which would be much more expensive. So we can approximate the system supply curve using that stacked bar graph. And so the market price here would then be calculated by the interaction or intersection of this supply curve with the demand curve. And I mentioned before, the sort of rule of thumb for electric power systems is that the demand curve is really pretty vertical, because demand is more of a constraint on the system. It's not really a market. I mean, to some extent in wholesale markets there is a market, but um, the ultimate consumers of electricity, which are people, aren't really exerting any sort of like price elasticity of demand. We expect that, in other words, we're not making a price conscious decision when we turn our lights on. And so this is really a constraint on the system. They have to meet demand, and so that's why the demand curve is up and down. And so the price of electricity here is set by the intersection of the supply curve and the vertical demand curve. So the market price here would be the value on the y-axis that is associated with this red dotted line. So if we have a higher price of natural gas, that actually deforms the shape of the system supply curve. The part of the curve that's associated with natural gas prices increases. Likewise, if we have a lower price of natural gas, which is what we have now in the United States, then the shape of the curve associated with natural gas plants gets lower, because the cost of producing electricity from those power plants is lower. So you have three different possible shapes of this curve, given three different natural gas prices. And here, note that the rest of the curve, the part that's associated with nuclear, coal, hydro, and oil, all stays the same. And so for these three different natural gas prices, for the exact same portfolio, system of generators, we get three different wholesale prices of electricity. So the last type of commodity that we're going to talk about is electricity itself. So far we've really talked about how commodities and commodity prices can be passed through to the price of electricity. And now we'll just sort of talk about electricity itself as a commodity, and how markets and prices for electricity work. If you're interested in this type of stuff, I would recommend taking the class I teach in the spring, which deals a lot with electricity markets. Now, this is sort of a foreign concept to a lot of people, because in North Carolina, our only interaction with our electricity provider is as retail customers. And we really don't have retail prices that fluctuate. In some parts of the country, you do have time of use retail prices that encourage people to reduce their consumption of electricity during peak hours by charging them more. And you might have seasonal changes in electricity prices too, where electricity is more expensive in the summer or the winter. But for the most part, retail electricity prices are specifically, or have historically been designed to be sort of artificially stable, and that's to protect individual consumers from having to worry about at any given moment what the price of electricity is. In most of the country, not North Carolina, our utilities, which we would refer to as retail distribution companies, interact in wholesale markets on behalf of their customers. So if you're Duke Energy, you become two separate companies. You become Duke Energy, the generator, who owns all these power plants, and those generators all sell electricity into the wholesale market. And then you become Duke Energy, the retail distribution company, and that part of Duke Energy would go on to the wholesale market and buy electricity at the cheapest price for its customers. And so this is a way of getting individual generators all across the country, or in certain regions, to actually compete with each other for the ability to sell electricity based on cost. So here's a schematic of how that works. you and I and everybody we know are at the bottom here. We're the retail customers, and we pay retail rates to a distribution company, and they deliver us electricity. Now, in North Carolina, the generators are also owned by the same retail distribution company, so that's what we call a vertically integrated company. They also own all the distribution and transmission. In most other parts of the country, we would buy electricity from a retail distribution company, but it would be their job to go onto a wholesale market and buy that generation specifically from generators. And they would pay a different rate. So the electricity is the same, right? The electricity is flowing from generators to retail distribution companies to customers. But distribution companies are paying wholesale electricity prices for the electricity on the market, and they're charging us retail rates. Retail rates are included, or in retail rates are included the wholesale rate, but also the cost of maintaining transmission and distribution systems and lots of other stuff. And retail rates are made to be artificially stable as well. So I mentioned, retail rates should always, in theory, be higher than wholesale rates because they include the cost of transmission and distribution and and other stuff as well. Um, actually, a reasonable way, even if we're talking about retail rates that change through time, like if you go out to California, everybody is pretty much on a time of use pricing system. And the goal of that is to really have retail prices reflect wholesale prices in a more controlled way so that you're exposing customers to the reality of how power systems operate. And that goes a long way in terms of getting customers to reduce consumption of electricity during high demand periods, shifting their consumption to periods when the price is low, and that could be extremely helpful for integrating really large amounts of renewable electricity. But if you look at the figures at the bottom here, on the left-hand side you have wholesale prices for electricity. And if you took a look at, if you wanted to, on average, sort of set the price of electricity here so that that retail customers were never experiencing any fluctuation in what the price of electricity was going to be, but you were guaranteed to sort of cover your costs, you would set it at that black solid line, which is a little hard to see, but the black arrow is pointing to it. The overall mean here is that black solid line. So that would be kind of like North Carolina, where the utility is experiencing the blue line, the blue time series, where the actual cost of providing electricity varies a lot, and in some cases can spike to pretty high levels, but it's only charging customers this mean amount, and it's set that price accordingly so that at the end of the whole time series, it's recovered its costs. A time of use pricing would be kind of like the red signal. It wouldn't be exactly reflective of wholesale prices, but it would be pretty close. There would be times where it wouldn't capture extremes, right? It wouldn't capture periods when the actual wholesale price goes really low or really high. That would still be filtered out. So you don't put customers in a situation where they are actually experiencing a spike in electricity here. So you don't want electricity customers to ever experience a situation where especially if you're a business and you can't predict this sort of thing, and you have limited means of adjusting your dependency on electricity in the short term, you don't want to put retail customers in a situation where they're experiencing potentially a price increase from $60 per megawatt hour to $180 over a very short period of time. So time of use prices still filter out a lot of those big spikes. So wholesale markets are really complicated. There's usually two different markets for selling electricity. One, a day-ahead market in which all generation is sort of scheduled in advance, and there's a day-ahead price associated with any generation that's scheduled 24 in advance. But inevitably, there's going to be some error in forecasting how much generation is actually needed. Or there could be certain contingencies that occur that increase or decrease demand for electricity. And so there's usually a second real-time market for electricity as well that's run every 5 minutes or even at higher time resolution than that in order to balance in real time supply and demand. And so the blue plot on the left shows day-ahead electricity prices, and the red plot on the right shows real-time prices. And you can see that they're pretty similar, right? Because what you end up having is, the changes in the day-ahead electricity prices are due to demand, but also what that really means is that the changes in demand are causing the system to rely on a different marginal unit or market clearing unit. So if in a peak hour of the day-ahead price is really high, that's because it's relying on a more expensive power plant. And in real time, even if you had a need for a very small amount of electricity, that demand would be met by that same, usually by that same power plant that's setting the market clearing price in the day-ahead market. So that's why in general, day-ahead prices and real-time prices look pretty similar in terms of their time series characteristics, or the overall signal, I guess I would say. But certainly there's more noise in the real-time market. And that's because things are a little more unpredictable. And because you are accessing, in some cases, a different pool of generators that can respond to demand. And one thing to note in particular, you have this period in the real-time market at about time period 100, where the real-time price of electricity actually goes negative. And what that means is that there's an oversupply of generation on the system. So there's too much electricity and not enough demand. And so the only way they can, and that, by the way, is causes pretty significant issues. Remember, we talked about how power systems are AC systems, and if you have generation that's above or below demand, that alters the frequency of the system, and you can get into situations where you deviate far enough from that you can cause instability on the grid itself. And so the market has to incentivize generators to curtail output or shut down if there's too much, too great of a supply of electricity. And the way they do that is by causing prices to go negative, which means if you want to sell electricity, you actually have to pay to sell electricity. And I've already sort of mentioned this stuff. In general, real-time prices and day-ahead prices track pretty closely, and that's because most of the time it's usually the same plant or a similar plant that's setting the market clearing price on each. Okay, that's it. I know that was kind of a long one, and I think that's probably because I have not done one of these lectures in a while, and I was a little rusty. So that's that, and next time we're going to talk about, we're going to move towards stochastic modeling, which should be fun. Okay, I'm going to post this on YouTube.